Hi, everyone. Welcome back to EGPGV. We're in our third session. We have a great session on research and volumes. We have three papers that are going to be presented today. So without further ado, let's go ahead and get to the first one. Our first paper is Evaluation of PyTorch as a Data Parallel Programming API for GPU Volume Rendering. It is by Nathan Marshak, Pascal Grosset, Aaron Knoll, James Ahrens, and Chris Johnson. So let's go ahead and get to the talk being presented by Nathan Marshak.
Evaluation of PyTorch as a data parallel programming API for GPU volume rendering. Data parallel programming has attracted considerable interest from the visualization community, and it has led to major software initiatives like VTKM. However, there has been relatively little recent investigation of data parallel APIs in higher level languages such as Python. Furthermore, machine learning frameworks exposing data parallel primitives such as PyTorch and TensorFlow have exploded in popularity. Therefore, the time is ripe to evaluate PyTorch as both an API for data parallel programming and as a way to implement data parallel scientific visualization algorithms. In this paper, we evaluate PyTorch as a data parallel API. We apply data parallel primitives in PyTorch to implement a proof of concept volume renderer for scientific visualization, and we also do a performance comparison of two distinct data parallel formulations of volume rendering implemented in PyTorch, and we compare them to each other and to VTK. Data parallel programming has its roots in the seminal work of Blalock, who, in his 1990 thesis, proposed a programming model for the famous connection machine supercomputer, and he presented a programming paradigm in which algorithms are expressed in terms of data parallel primitives, that by definition can apply an operation to a size n array in O of log n time, assuming an unlimited number of processors. Such primitives are intended to abstract away implementation details such as scheduling, synchronization, and communication that are specific to each parallel or distributed architecture being targeted. Nowadays, what you'll find is that these aren't directly implemented in hardware. What people do is that they call the GPU through an API like Thrust, which is a common library in CUDA. There were also previous attempts to have a data parallel programming API that Python users could use, notably Copperhead. However, that's no longer actively maintained, and there hasn't been all that much investigation of data parallel programming APIs in higher level languages like Python, especially for visualization. On the topic of visualization, a modern data parallel API that is currently under active development is VTKM, and its purpose is performance portability at exascale. Two well-known works in visualization that were later folded into VTKM were volume rendering via data parallel primitives by Larson et al. In 2015, that's on the left, and volume rendering with data parallel visualization frameworks for emerging high-performance computing architectures by Schrutz and Ma, and that was also done in 2015. So these works are relevant because we're also trying to do volume rendering using data parallel primitives. However, we could not simply take the pseudocode from these prior works and copy and paste them into PyTorch, and the reason why is because PyTorch lacks the ability to compose a data parallel primitive with a user-supplied function and or binary operator. So what you see on this slide, highlighted in yellow, are situations in which these two past works use a data parallel primitive composed with a user-defined function or binary operator. PyTorch does have reduce add as its own standalone function. However, it doesn't have any of the other highlighted functionality because it doesn't let you compose a data parallel operator with a user-defined function, or binary operator, or flag denoting inclusive or exclusive scan. Our work is most closely related to what computer vision authors have come up with over the past couple of years. That's where our array of arrays and scan and reduce data parallel formulations come from, and we'll talk about what those are later. Computer vision works focus on machine learning techniques that utilize a differentiable implementation of absorption emission volume rendering. By contrast, what we're doing is that we're investigating PyTorch as a tool to do data parallel programming. We're also comparing different data parallel formulations that the computer vision people have come up with against each other. These computer vision people, they're mostly going to be focusing on comparing their computer vision techniques as opposed to comparing which data parallel formulation is more performant for rendering in PyTorch. Finally, we compare against VTK using their OpenGL backend, whereas computer vision people, they're going to be comparing against previous, perhaps off-the-shelf computer vision techniques, which may not even involve volume rendering, as opposed to comparing against an off-the-shelf scientific visualization tool. Finally, just some notation. L is the radiance, G is the glow or emissive term, and alpha is alpha. So the first data parallel formulation that we'll consider is called scan and reduce, or SR, and the idea is we evaluate the Riemann sum that approximates the volume rendering integral by stacking all of the alpha values into a gigantic array, and also stacking all of the G or glow emissive values determined by the transfer function into a gigantic array. And what you do is that you do a scan, a reduce, an element-wise multiply, and another reduce, and then you get your answer. This approach was used in computer vision at least as early as the Platonic GAN paper. However, this approach certainly isn't very common in visualization, at least to our knowledge. We obtain the so-called gigantic arrays that I was talking about earlier that contain the required alpha values and glow values by sampling the volume using PyTorch's grid sample function. A sampling grid is pre-computed by creating a 3D array of uniformly spaced coordinates, then applying a perspective warp via scaling the sample positions by a factor proportional to their camera space z coordinate. Whenever the viewpoint is changed, the sample positions must be updated accordingly by applying an appropriate transformation matrix, and this will become important to think about once we look at the performance benchmarks. And next up is what we call TSR, which is short for tiled SR, or tiled scan and reduce, and this strategy was originally, at least to our knowledge, used by the NERF, or Neural Radiance Field paper in 2020, in order to reduce memory consumption. And it's pretty simple. It's the same as the scan and reduce approach that we saw earlier, except you divide the image into 4 equal-sized quadrants, then you perform scan and reduce in serial on each of the quadrants. For this paper, for our benchmarks, we apply the perspective warp that's required for perspective projection once per quadrant at render time, as opposed to being a pre-compute step like before when we didn't tile. There's probably a way to avoid applying it once per quadrant at render time, but we consider that to be future work. The last data parallel formulation that we will consider is the array of rays, or AOR formulation for short. In the computer vision literature, this was used at least as early as neural volumes in 2019. This is also very closely related to what Schrutz and Ma in 2015 in their work on data parallel volume rendering for structured volumes. It's very closely related to what they refer to as ray marching. What you're seeing here, without going into all the details of the pseudocode, is that we have an approach that very much resembles a traditional back-to-front compositing loop for volume raycasting. However, unlike GLSL or CUDA, PyTorch has no notion of individual fragments or thread IDs. Instead, we perform our operations over entire multidimensional arrays. So just to give you an idea of how this works, if you look at line 3, we do the ray AABB intersection, and we store the result in tmin and tmax. The difference between this and maybe a typical implementation you would see in GLSL is that tmin and tmax are not scalars. They're actually 2D arrays that are the size of the frame buffer, and they're storing the minimum maximum hit distance for every ray in the frame buffer at once. Similarly, on line 6, where we store into P, maybe if you were programming in GLSL, there would be a vec3, a 3D position where you'd store where you want to sample next. What we do here is that we're storing a big, gigantic array that's, the height's the size of the frame buffer, the width is the size of the frame buffer, and maybe the depth of the array is 3. And what we're doing is that we're storing the position that we're going to sample next on every ray that's being considered. We compare these approaches against each other and against VTK using a desktop with an RTX 2070 GPU that has 8 GB of onboard memory, and also on a server with an RTX 3090 GPU that has 24 GB of VRAM. When we compared against VTK, we used its OpenGL backend called via its Python API. The VTK measurements were made on the RTX 2070 only because the server is headless, and therefore we couldn't create a window. We performed benchmarks on an 1024 cubed float 32 volume that comes from the Rayleigh-Taylor instability simulation dataset, and we also did benchmarks on the 512 cubed magnetic reconnection simulation dataset. We only show the Rayleigh-Taylor dataset results in this presentation and in the main paper for the sake of space and or time. However, we do have the results for magnetic reconnection in the supplemental material for the paper or in the backup slides of this presentation. For both datasets, we also test downsampled versions in order to evaluate scaling with volume size. What you see here are the results from our tests of individual data parallel primitives in PyTorch. So what we're really doing is that we're testing simple mathematical operations over arrays, and we wanted to do this to make sure that at least the primitives perform decently in PyTorch before we started getting our hands dirty with volume rendering. So on this chart, you'll see time on the y-axis in milliseconds using a log scale. And on the x-axis, we have the number of array elements, because these data parallel primitives, they're operations over entire arrays, as opposed to just operations on a scalar. So if you would please direct your attention to the blue and dotted blue lines, those are our results for 50 repeated multiply adds, where we define a multiply add as a scale of an array by some scalar, and an addition of that scaled array to another array, both of which contain random floating point numbers. What we can see is that the performance in scaling for multiply add is pretty similar across both PyTorch and Thrust, Thrust being the native CUDA library that's kind of a decent baseline for data parallel programming on a GPU, and obviously they're pretty close. Now, let's take a look at the yellow line and the yellow dotted line. That's the scan operation, and that's considered to be crucial to a very large number of data parallel algorithms. For small array sizes, Thrust has a clear advantage. However, for larger array sizes, around 10e7, 10e8 elements, they're pretty close. If you would kindly look at the red line and the red dotted line, those are results for reduce. It's another very common data parallel operation. For smaller array sizes, once again, Thrust beats PyTorch, but what's very interesting is that once we get to larger array sizes, PyTorch starts pulling ahead, and in fact can beat Thrust by about an order of magnitude at the largest array size tested. The one primitive that we tested that isn't really, strictly speaking, a data parallel primitive is sort, but we kind of just threw that in there just because it's a function that you oftentimes call. And what we found here is that sort in Thrust is about an order of magnitude faster than PyTorch, and it seems more scalable because our GPU ran out of memory at the largest array size tested. That's why, sort of at the very far right of the graph, there's one data point for sort that's not there. All in all, performance of the data parallel primitives that we needed was pretty comparable across PyTorch and the baseline, which is Thrust, except for sort. And now for some actual volume rendering results. What we see here on the y-axis is VRAM usage in megabytes, and on the x-axis, volume dimensions. Now you might recall that the Float32 Rayleigh-Taylor instability volume has a native resolution of 1024 cubed. However, we downsampled to 512 cubed, 256 cubed, and 128 cubed, not only to test scaling with volume size, but because some of these approaches don't actually work on larger volumes. You've probably already noticed that there is only one data point for the 1024 cubed volume, and that's VTK's OpenGL backend. And the reason why is that all of the PyTorch-based data parallel programming approaches consume so much memory that they simply don't scale to that size, which is a pretty significant limitation, and we'll discuss that in more detail later. Another thing to note is that if you take a look at the solid red line, which is the scan and reduce approach on the RTX 2070, there are only 2 data points. And the reason why is that that approach has the worst memory scalability, and that can't even render a volume at 512 cubed. It can only go up to 256 cubed, at least in our tests. What you'll see is that tiled scan and reduce is more efficient than scan and reduce, which is expected because splitting the volume into smaller subvolumes is a hack that you can do effectively to save memory. Finally, the array of arrays approach is the most memory efficient, and we'll discuss why in the evaluation. However, all of these approaches are still more memory intensive than VTK's OpenGL backend, which is why none of them can scale to 1024 cubed, despite the fact that VTK has no problem doing so. And one of the reasons why is that all of these approaches require storing sample positions in memory in large arrays, and also because our approach is based on pre-classification of the volume. That means we do the transfer function lookup before we apply all of these data parallel primitives. And as a result, we have to store gigantic RGBA volume in memory as opposed to just storing a scalar volume of the original data values. The RTX 3090 has more video memory than the 2070, so that explains why SR on the 3090 can scale to 512 cubed. And here are the same results on this next slide, but for render time in milliseconds on the y-axis instead of VRAM consumption, and the same caveats apply. In some places, we weren't able to record data points because, as you saw earlier, we ran out of memory. So what you can see here is that if you look at the red lines, the solid red line, the dotted red line, that's scan plus reduce, that was generally the fastest of the sort of PyTorch data parallel approaches. But of course, as you saw on the previous slide, those two were the least memory efficient. So in order to try to make scan and reduce more memory efficient, you can take a look at the yellow line, that's tiled SR. So that does better, and that, for example, allows us to scale to 512 cubed on the RTX 2070, but that comes at a performance penalty. As you can see, the render time's longer. These lines are higher than the red ones. Still more memory efficient is the array of arrays, or AOR, and those are in blue. And as you can see, the blue solid line and the blue dotted line are above the yellow lines. So that's even more memory efficient, but there's a penalty for render time. Interestingly, at the 512 cubed resolution, at least on the 2070, array of arrays does slightly better than tiled SR. One thing to note, though, is that despite all the things that we tried, an OpenGL backend on VTK still outperforms all of these PyTorch-based approaches. And in the worst case, the PyTorch-based approaches are maybe 1.5 orders of magnitude slower. Finally, we have some profiling results. The important thing here is that we wanted to figure out how much time was spent calculating sample positions, because if you recall, for the scan and reduce approaches, or the tiled scan and reduce approaches, we have to recalculate an array of sample positions, all of them in 3D space, every time we move the camera. And these profiling results account for that. For the most part, sampling the volume is the dominant cost in render time, except for tiled scan and reduce at the 1024 squared resolution. Now for the evaluation, we found that most individual data parallel primitives tested, with the exception of sort, perform well. However, PyTorch has limitations in terms of expressiveness because, as we discussed in the evaluation, we couldn't implement some of these less trivial algorithms that Schrutz and Ma or Larson et al. Came up with, because we don't have a map functor capability in PyTorch, and more broadly speaking, we can't give an arbitrary user-defined function and or binary operator to these data parallel primitives as an argument in PyTorch. We found that render times are promising for an initial proof of concept because they are within about 1.5 orders of magnitude of the baseline set by VTK. However, memory consumption is the bigger problem for scalability, and the reason why is because for scan and reduce, I'm assuming that the Nyquist-Shannon sampling theorem holds, for an image size of m squared and a volume size of n cubed, the array of samples that we have to give to the scan and reduce is of size O of m squared n elements, which is really big. We saw that tiled scan and reduce and array of arrays can reduce memory consumption. Array of arrays in particular is nice because the array of sample positions depends on the resolution of the image and not on the size of the volume. However, as we saw, they're slower. And even with these two approaches, pre-classification means that they consume much more memory than VTK, and as a result, none of them could render the full 1024 cubed volume, for example. What we set out to do was that we wanted to evaluate PyTorch as a data parallel API, then we wanted to apply it to implement a proof of concept volume renderer, then we wanted to benchmark different data parallel formulations against each other and against VTK. What we found was that most data parallel primitives in PyTorch are performant, but expressiveness is limited because we don't have the ability to compose data parallel primitives with arbitrary user-defined functions and or binary operators. It turns out that in terms of performance, we were within about 1.5 orders of magnitude of VTK in terms of speed, but the bigger problem for scalability is memory usage. And as a result, we still can't scale to large volumes and or image sizes. Future work includes deeper investigation of PyTorch performance, investigating more ways to do tiling, and doing what some authors do, which is bricking in the z-dimension. And finally, more investigation of primitives, different algorithms, and also different kinds of programming languages and frameworks. This work was brought to you by Los Alamos National Laboratory, Intel, the NIH, and the DOE. Please see the paper for a full list of references.
All right. Thank you. That was a very interesting talk. If you are watching live, I certainly encourage you to type in questions in the Discord. Keep in mind that it might take a minute before we actually are able to see it. So, type early, type often. We've had a few questions come in. So let's go ahead and get started. One of our first questions was from Hamish Carr. Do you have any intuition about why the PyTorch reduction is better?
That's a good question, because it probably shouldn't be better, because most of these primitives that PyTorch sort of exposes are really just a Python wrapper for thrust. So I would have to take a look at how that particular primitive is implemented. I suppose the worst case is somehow I measured it wrong, but I would have to take a closer look at that. Sorry, I don't have a great answer. It is weird.
Okay, so a follow-up question to that by Sebastian Weiss. All the other plots show linear scaling once the GPU is completely utilized, but not the PyTorch reduction.
Yes, so that is a bit weird. And I guess I'd say the same thing. Like, I'd have to take a look at how the PyTorch reduction is implemented, which is, it calls thrust, but maybe they call thrust in a way that's different from how I called it. And I'd have to take a closer look to really be able to answer that question.
Okay. I'm seeing a few questions about different comparisons. So Hamish sort of asks again, have you considered comparing against CUDA, I guess a CUDA-based implementation as well as the thrust implementation?
Yes, you could. The reason why we compared against thrust is because we were looking at data parallel APIs, and thrust sort of exposes something that sort of looks like these primitives that Ballock talks about. And one of the things that thrust at least tries to promote is sort of composing them and programming in that fashion. It is possible that CUDA would be faster, but we were kind of going for a comparison against some baseline that already exists, as opposed to trying to get the fastest thing possible.
Okay. There were some questions on comparing to different implementations. Stefan Zellmann mentions that there's a lot of memory consumption that is being done with a PyTorch implementation. How would that compare to a naive CUDA kernel, where you have 1 ray per thread, and using 3D or 2D textures for volume and transfer function?
Yes, as we mentioned during the presentation, sort of memory consumption, having a very large view-aligned grid is probably the main practical limitation of this work. My guess would be like the naive CUDA kernel kind of approach, where you're just doing ray marching. It's probably going to look fairly similar to the results we showed for VTK, at least in terms of memory consumption, because in both cases, you don't have to sort of store a very large view-aligned grid. You also don't have to sort of pre-classify the transfer function and store it in a gigantic RGBA volume. But maybe a naive implementation in CUDA wouldn't be quite as fast as what's in VTK because there may be optimizations in that particular bit of VTK code. But I'd imagine that, if you do it in CUDA the naive way, it would be better for very similar reasons why VTK compares favorably to what we did.
Okay, and we have another question from Sebastian Weiss. Have you considered replacing some of the operations by custom PyTorch extensions like the rate generation?
Yes, we could, and actually, sort of some recent work that came out was that the PyTorch 3D library now supports volume rendering in order to support work like the NeRF or the neural radiance field. But at the time, that hadn't been released yet, at least when we did sort of the original work. And the other thing is, right, we can always sort of implement sort of custom operations in PyTorch, using CUDA. But what we were trying to do is that we were trying to see if we could use PyTorch as sort of a data parallel API that you could call from Python, because we wanted to figure out if, we could use it to do data parallel programming in a way that's maybe less labor intensive than, writing something custom in CUDA. And, there had been attempts to do this before, like the Copperhead library, but that stopped being actively maintained. So we were hoping that PyTorch maybe would be something we could use as a data parallel API in Python that is likely to, stick around and not go away. If you have to write a lot of custom code, maybe like in C++ or CUDA, in some ways that might defeat the purpose of trying to find this API that you can use in Python and that allows you to stay in Python. That being said, something like rate generation in a custom CUDA kernel, that might be very helpful, because maybe if you could implement at least some parts in CUDA, you could get around this problem of having to store a very large axis aligned grid with all your samples in it.
Okay, great. I think we run out of time for this paper, but I'd like to thank Nathan once again for a wonderful presentation and a great Q&A. All right, we're now moving on to our second talk for our third session at EGPGV. This talk is titled RTX-Accelerated Empty Space Skipping using Triangulated Active Region Boundary Geometry. This paper was written by Ingo Wald, Stefan Zellmann, and Nate Morrical.
My name is Nate Morrical. I'm a graduate student from the University of Utah and a member of the Scientific Computing and Imaging Institute. And today I'll be giving a talk on our work titled Faster RTX-Accelerated Empty Space Skipping using Triangulated Active Region Boundary Geometry. This work was done in collaboration with Ingo Wald and Stefan Zellmann. The motivation of our work comes from the desire to visualize large volumetric datasets at interactive frame rates. These datasets are constantly increasing in size, so in order to visualize these datasets interactively, only a select few representative samples can be taken per frame. Fortunately, many of these volumes we would like to visualize contain a large amount of empty space, and we can use that to our advantage by avoiding sampling these regions, which otherwise introduce unnecessary wasted work. However, efficiently identifying and skipping over empty regions of the volume is still an active area of research, with many challenges that require additional consideration. First, there are many different volumetric representations that need considering, from structured grids to semi-structured adaptive mesh refinement data, cleared to fully unstructured meshes. Second, the actual structures within the data that we would like to render are often very thin, wispy features, and with a very high frequency, which in turn requires a very accurate estimation of empty space. And last but not least, it's very important that whatever space skipping strategy we deploy that we're very careful to minimize any overhead introduced in that process. If the space skipping process ends up being more expensive than the work you save by not sampling empty space, then you'll only stand to damage the visualization interactivity. And this overhead can come in many different ways, from additional depth complexity marching through that space skipping structure during rendering to the actual construction and update time of that data structure itself, say during transfer function editing. So we want to be able to reduce this overhead as much as we can so that we have a net positive impact on interactive visualization. Not too long ago, state-of-the-art in empty space skipping involved leveraging triangle rasterization hardware to compute per pixel lists of active ray segments by rendering occupancy geometry. This is exactly what the Sparsely paper by Hadwiger et al. Proposed in 2017, where the authors there proposed to then integrate these active ray segments from front to back, implicitly skipping empty space in that integration process. However, later in 2019, we began to see commodity GPUs with dedicated ray tracing hardware, which accelerate both ray triangle intersection tests and bounding volume hierarchy traversal in that hardware. This led to 2 more recent papers on space skipping, both of which use this hardware to further reduce overhead and improve space skipping accuracy. The first of these works was that by Ganter and Mansky, which demonstrated that if a BVH is constructed over the active macrocells of a volume, rays can then be traced over this BVH in hardware as a substitution for the triangle rasterization step by Sparsely, in order to compute those per pixel integration segments. Their work successfully demonstrated that RT cores could be used as an alternative to rasterization hardware for space skipping, and the results outperformed Sparsely by nearly 40% on the volume shown in their teaser. Almost simultaneously, my colleagues and I were also exploring a similar application of RT cores, but for both space skipping as well as adaptive sampling, and for unstructured volumes instead of just regular grids. Unlike the work by Ganter, the macrocells in this work were constructed using hardware-accelerated triangles as opposed to custom user geometry, and this further improves the performance of RT core-based space skipping by avoiding the back-and-forth execution of ray tracing cores and software execution on the streaming multiprocessors of a GPU. Although a great amount of progress has been made in using ray tracing hardware for space skipping, there's still room for improvement that we focus on in this work. First, it's often the case that constructing the occupancy geometry itself is a bottleneck. In the case of Ganter and Mansky, voxels must be clustered on transfer function edits, and that clustering step can be very expensive. In the case of our prior work, we stored minimum and maximum data values per macrocell, and in parallel, we'd mark these macrocells as active or inactive in order to avoid the expensive clustering step. However, this came at a trade-off to depth complexity during runtime, as rays would need to still march over these macrocell regions, regardless of whether those regions were active or not. In this work, we will primarily be focused on building off the work by Ganter and Mansky, and focus solely on regular grids and space skipping, rather than unstructured data or adaptive sampling. Our contributions include a method to avoid the costly clustering used by Ganter, while also culling inactive geometry from the BVH to avoid unnecessary depth complexity. Our occupancy geometry construction is done entirely on the GPU, meaning that there's no overhead in copying data back and forth between the host and the device when the transfer function changes. And finally, we further optimize the use of hardware-accelerated ray triangle space skipping by removing unnecessary internal triangle faces that otherwise increase depth complexity of the space skipping process. Our algorithm consists of 3 major steps: an initial setup step before rendering starts, a building and rebuilding step of the space skipping data structure for when the transfer function changes, and a final step which involves using that structure for space skipping during volume rendering. We start out by defining a macrocell grid where each macrocell contains a k by k by k grid of voxels. We then compute the minimum and the maximum of the voxel values contained in each macrocell, and we cache these min and max values in the corresponding cell. Finally, we pre-allocate a vertex buffer that we will later reference for our space-skipping triangle geometry. This vertex buffer is made to contain all of the possible vertices of the ladder triangles, and although at first this sounds to be a memory prohibitive thing, the footprint of this vertex buffer isn't actually so bad, since they're just the vertices of the macro cells rather than the underlying voxels. Next is the building step. This process occurs every time the transfer function is set or modified. When the transfer function is modified, we classify all macro cells as either being active or inactive. This is done by searching for a non-zero occupancy value in the transfer function between our minimum and maximum data values cached in the macro cells. This process is done in parallel with one CUDA thread per macro cell. Once we know which of the macro cells are active and which are inactive, we need to compute the triangle indices to use for space skipping. Our ultimate goal is to only place triangles between active macro cells and inactive macro cells. To do so, we execute the same CUDA kernel 3 times, one to generate the x dimension triangle faces, one for the y dimension triangle faces, and one for the z dimension. For each macro cell, we generate a thread. For a given macro cell and a dimension, we check if the current cell, as well as the previous cell in that specified dimension, if those are active or inactive. If the current cell is active and the previous cell is inactive, or the other way around, we insert a quad face into our space skipping geometry. This quad face is made to represent, or it's made to reference the vertices in that previously allocated vertex buffer, and then we triangulate that quad so that it can be hardware accelerated using RT cores, and we insert those triangle indices into a list of triangle indices using a global CUDA atomic. So in the end, here's what those triangles end up looking like on a couple different data sets. These triangles only exist between inactive and active macro cells. So the majority of the triangle faces here only exist on the boundary with little to no internal triangle faces. From here, we pass these triangles to the RTX builder to obtain a BVH compatible with hardware accelerated traversal. As our final step, we will use this structure for empty space skipping. We begin by tracing a view-aligned ray through the BVH containing these boundary faces, finding where our array intersects this boundary. When backface culling is turned on, the intersection distance reported by hardware indicates where to start integrating the volume, and with front face culling on, the reported intersection distance indicates where to stop integrating the volume. So from here, we deploy traditional ray marching to integrate between those two intersection distances. So that's the method. We do an initial step to generate this macro cell data structure and triangle vertex buffer data. From there, we classify macro cells in parallel as active or inactive, and then we generate triangles between the active and inactive macro cells. From these triangles, we generate an RTX BVH, which we then use to compute per pixel integration segments during traversal. Next, to evaluate our approach, we tested on a couple different datasets of varying sizes. These are what you're seeing right now are a set of heat maps measuring performance, where on the left, space skipping is disabled, and then on the right, we enable our space skipping scheme. So on the far left, we have the flower dataset, which is also used by Ganter and Mansky. In the center, we have this heptane dataset, and then on the right is the Richmeyer-Meshkov dataset. All of these datasets contain a large amount of empty space, and as shown here, our space skipping scheme is quite effective in avoiding expensive sampling of these empty regions. We also tested against a 4x subsampled version of the full DNS dataset, shown here. The center of this dataset is often rendered as entirely transparent, and when using our approach, visualization interactivity of this dataset is greatly improved. Using these datasets, we compare both build times and rendering times against the work by Ganter and Mansky. These are the same tables shown in our paper, but for now I'd just like to highlight some of the more major findings. So first, the table on the left are results of the prior method by Ganter and Mansky, and then the results of our method are on the right. The far right column of both of these tables records the total data structure build time, assuming the end user were interactively editing a transfer function. In every case we measured, our findings showed that our build time outperforms the prior work. Our method also scales much better to larger datasets, with the LLNL Richmeyer-Meshkov building an order of magnitude faster with our method. As expected, build time for both techniques improve also as macrocells grow larger. In terms of rendering time, our technique also outperforms the prior work in all of the cases that we measured. Shown here is a table comparing the work by Ganter and Mansky on the left versus ours on the right. And at 1 ray per pixel, both techniques achieve interactivity on most of these datasets. However, our approach is often able to achieve roughly double the performance on the larger datasets. We do see diminishing returns with smaller macrocells though, as shown in the k=8 configuration. We also see a loss of performance in the k=32 configuration, suggesting we're unnecessarily integrating some empty space there. So in general, k=16 seems to be a good compromise between these configurations, at least for the volumes that we tested on. So in conclusion, this work presents a method that improves upon prior RTX-accelerated space-skipping works. Our approach works by building BVH only over the boundary geometry between active and inactive regions, which in turn reduces depth complexity of the space-skipping process. This results in fewer rays being traced and less triangles to test for intersection against. Finally, we present a GPU-accelerated method for constructing this boundary geometry to make for more fluid transfer function editing. One key limitation of this current work is the inability for the current data structure to support adaptive sampling, which has previously been shown to enable another level of accelerated volume rendering. We believe that our data structure could be modified to support adaptive sampling as well, but this would require further investigation. Another limitation of this work is that so far we've only explored structured datasets. As shown by the prior works, RT cores can accelerate space skipping of other kinds of things like AMR datasets and unstructured datasets, but this would require further investigation. Finally, we believe that it would be interesting to explore the use of BVH refitting as an alternative to rebuilding the BVH for each and every transfer function edit. It's possible that refitting could be used during transfer function edits, followed by a fresh rebuild for subsequent camera movement. Anyway, thank you all for listening, and feel free to reach out if you have any questions.
Excellent, thank you. That was a great talk. We have Stefan Zellmann here to answer any questions that you may have. So if you are watching this live, please feel free to type questions into Discord. While we wait to see if any questions come in, Stefan, I have a question for you. So at the end of your talk, you sort of conclude that k=16 seemed to be a good number. As I watched those, looked at the numbers, it looked like larger values of k seem to work better for larger data sets. Can you comment on that?
Yeah, that's a good question. I mean, this is very data set dependent, right? Very much dependent on the frequencies that you actually observe in those data sets. And the data sets that we tested with, like the Richtmeier-Meshkov data set, have like very high frequencies in certain regions. And this is not a my answer basically being that this pretty much depends on the spatial configuration of what you're doing. Like for the data sets that we've tested with, and those were actually only 4. We found that k=16 was the best compromise, but in general, it is really hard to tell only from that tiny sample size, actually.
Fair enough. So maybe more testing to figure out if there's a better, more accurate way of doing the K.
Configuration,
yeah. So another question I'll throw at you is that the title of your paper is specifically for RTX-Accelerated architecture. How generalizable is this work for other architectures or just general volume rendering?
Like this is pretty crafted towards RTX, and that we're doing, and that we're in particular using the triangle geometry code path of RTX. Like when you have a look at the related work, for instance, by Ganter and Mansky, they used user geometry RTX-Accelerated, the user geometry RTX-Accelerated code path, where you have this back and forth between shader cores and RTX cores. So this is an optimization that is quite particular to RTX, where you don't have that back and forth because the whole pipeline stays in a hardware accelerated mode. So if you're like on an architecture where you don't have like hardware accelerated triangle intersections, things might be different. Like a user geometry AABB intersection might actually be more efficient than that. So this is, on the one hand, this is quite particular. On the other hand, the idea that you have those active regions and then just compare, like, do the sweep along the 3 dimensions and the X and Y and Z dimension, then compare the previous and the current cell and their class, like their occupancy class. This is actually quite general. Like, this is the problem that space skipping state of the art try to solve in the past years. And this is actually something that is quite general, in my opinion.
Yeah, I actually, when I saw this work, I thought it was a lot more generalizable than RTX. I mean, certainly once it gets to BVH, yeah, that's pretty RTX specific. But intersecting triangles is one of the basic rendering operations that pretty much any approach is going to have. So I thought that was really great to be able to very quickly come up with a very small geometry to find entry and exit points in pretty much any geometry that you have.
Well, I mean, you're not restricted to BVHs. Like, what we're using is actually like this is not even an ABVH. Like, they don't overlap. Like, our macro cells don't overlap, and so the domains that we built the BVH over don't overlap. So you could, in general, use something like a KD tree or like a different acceleration data structure to do the build and also to perform traversal. So in this sense, this is actually a pretty general method. Yes. So
yeah. All right. If there are no further questions coming in, let's go ahead and thank our speaker again. All right, now we can move on to our third talk for the volume session at EGPGV. This talk is on performance trade-offs and shared memory platform portable implementations of a Stencil kernel. The authors are Wes Bethel, Colleen, Heinemann, and Talita Perciano. And so without further ado, let's go ahead and take it away.
The increasing prevalence of devices like GPUs, TPUs, FPGAs, as well as CPUs of increasing concurrency marks what we might refer to as the era of heterogeneity. In this environment, we'd like to write our code once and then hope to have it run efficiently and in parallel on many different devices. The software landscape for achieving platform portability is diverse and is a moving target. For CPU platforms, there are approaches like POSIX threads, OpenMP, VTK-M, and others, where you write code once and it runs in shared memory parallel fashion on different types of multi-core CPUs. On the GPU, you can write code in CUDA, but then it only runs on NVIDIA GPUs. There are other options like OpenMP with its device offload capability, SYCL, OpenCL, VTK-M, and so forth. Each of these has strengths or weaknesses, which all present design choices. Beginning with our code, which is a straightforward stencil-based convolution kernel, we use OpenMP loop parallelism for shared memory parallel use on multi-core CPU platforms. OpenMP now provides a pathway for running on GPUs using what is known as device offload. The basic idea is that you use pragmas to indicate what segment of code you want to run on the GPU. And this code, along with whatever data is needed for the computation, is offloaded to the device. The other pathway we use in our study is VTK-M. VTK-M is a library with an API for building algorithms using data parallel primitives, and that also supports numerous parallel backends, including OpenMP, TBB, CUDA, and others. In our study, we configured VTK-M to use OpenMP for its parallel backend on CPUs. And for use on the GPUs, we configured VTK-M to use CUDA as a backend. In all of these configurations, the idea is that from one code base, you code to the OpenMP model or the VTK-M model, and then these different codings without further modification on the user side are then run on different back-end devices. In our study, we're interested in better understanding the overhead cost associated with platform portability in these two parallel capable platform portable coding environments. In the Stencil kernel, the output at each pixel location I, or grid point I, is the weighted average of nearby input pixels that lie within the Stencil window. We use Gaussian filter weights, which give more weighting to pixels near the center of the Stencil window and less weight to those further away. Because the focus in this study is more about the methodology and approach for measuring performance differences of two different platform portable environments, the algorithm we use here is a well-understood Stencil kernel. This type of computational motif is present in many different algorithms important to the visualization, analysis, and data science communities. This listing shows the basic implementation of the 2D Stencil computation. A doubly nested set of loops iterates over the Stencil window and accumulates the product of the Stencil weights and the associated input mesh points. This illustrative example has two simplifications. First, it ignores the boundary conditions, which occur when the Stencil window straddles the boundaries of the input mesh. Second, it assumes that in all cases the sum of filter weights is 1.0, which may or may not always be the case. This listing shows two different ways of using OpenMP for platform portable parallel code. In the first example, which we refer to as coarse-grained parallelism, the pragma shown on line 2 indicates that the loop starting on line 3 is to be parallelized. Inside the loops is a call to the Stencil computation from the previous slide. The idea is that we're doing that particular Stencil computation in parallel through loop parallelism. We refer to this configuration as coarse parallelism because each row of pixels is being processed separately and in parallel from all other rows of pixels. The second example shows what we refer to as fine-grained parallelism. Again, a pragma on line 8 indicates that the loop starting on line 9 will be parallelized. In this case, that one loop iterates over all pixels, and so the computation for every pixel will be done in parallel rather than grouped into rows of pixels, as was the case for the coarse-grained parallel example. In the VTK-M environment, one of our two implementations builds on VTK-M's field map worklet. This worklet is executed in parallel across all points of a mesh, similar in concept to our fine-grained OpenMP parallel code. Inside our field map worklet code, we're handed a single 1D index by VTK-M, which we first convert to I and J indices in lines 10 and 11. Then we perform the usual Stencil computation in lines 13 through 16, and then we assign the computed result to the output mesh on line 17. The second VTK-M implementation builds on the point neighborhood worklet. Like the field map worklet, the point neighborhood worklet is invoked in parallel across all mesh points. Unlike the field map worklet, this worklet is handed a set of indices that describe where in the mesh the worklet is operating. Lines 5 through 8 show the Stencil computation where the loops iterate over the indices provided by VTK-M. Another key difference between the field map and point neighborhood worklets is in that the point neighborhood worklet code must go through a helper method to access data in the source mesh. As we shall see in the results discussion, this approach for accessing data in the source mesh might cause some problems for compiler vectorization. The focus of this study is on two key questions. The first is in discovering what performance differences might exist between the OpenMP and VTK-M implementations on the CPU and GPU platforms. The second is in characterizing the nature of those performance differences. We made use of the GPU nodes on Cori at NERSC. Those consist of Intel Skylake processors and NVIDIA Tesla V100 GPUs. The software environment consists of the tools needed to produce parallel code for both the CPU and GPU and to collect hardware performance counter data. The source data is a slice of 3D micro CT data, a sample of sandstone, obtained at the Advanced Light Source at Berkeley Lab. We ran a configuration of the C++ code in serial just to have a baseline, and it's shown here in the leftmost column. We collected several different measures, including runtime, along with hardware performance counter data, the number of instructions executed, the number of scalar and vector floating point operations, a measure of vectorization, cycles per instruction, shown as CPI, and cache miss ratios for L2 and L3 cache. The remaining columns show parallel execution for OpenMP and VTK-M methods. Note that this study is not a scaling study. Because the Stencil method is well understood, we chose a modest level of concurrency with the intent of revealing potential sources of overhead, as indicated by performance measures. A first observation is that both OpenMP versions and the VTK-M field map worklet codes have similar performance characteristics in terms of runtime and number of instructions executed. The VTK-M's code instruction count is higher by about 5 to 8% compared to the OpenMP code, but it's not significantly higher. All three of these versions are showing about a 7.5x speed up when run on 8 cores. This is a respectable level of performance, nearly linear speed up without too much overhead getting in the way. Comparing these three to the serial run and looking at the instruction count, we see that the two OpenMPs and the VTK-M field map have elevated instruction counts. This is the cost of overhead of parallel code in these two programming environments. A second observation is that the VTK-M point neighborhood worklet runs about 32 times slower and executes about 18 times more instructions compared to the other methods. We also see that the CPI on these instructions is about twice as expensive as those executed by other methods, about 1.3 versus 0.6 to 0.7. While we don't know exactly what these extra instructions are looking at, just by looking at this data, we can infer that this is the overhead cost of VTK-M preparing the data and metadata needed for each invocation of the point neighborhood worklet in this problem. A third observation concerns the vectorization level. We see that the point neighborhood vectorization level is 0. This is due to the fact that the compiler vectorization is defeated by the point neighborhood worklet's use of a method to access source field data. On the GPU, we collected 3 performance measures using NVProf: runtime, number of instructions executed, and global hit rate, which measures cache utilization. There, higher is better. A first observation is that both OpenMP versions show essentially identical performance to 2 significant digits. A second observation is that compared to the OpenMP offload versions, the VTK-M field map worklet runs about 71 times slower while executing about 381 times more instructions. A third observation is that the VTK-M point neighborhood worklet runs about 133 times slower and executes about 1475 times more instructions compared to the OpenMP offload versions. Both VTK-M versions show better cache utilization numbers, but these can't overcome the fact that both VTK-M versions are executing way more instructions than the OpenMP versions. The VTK-M field map workload implementation allows user code to directly access the mesh, which creates opportunity for good vectorization. On the CPU platform, this version performs about as well as the OpenMP versions, but on the GPU platform, it runs significantly more slowly due to what appears to be executing many more instructions. These are most likely the result of the overhead of setting up and running worklets in CUDA's threads. The VTK-M point neighborhood worklet makes it easy for user code development since VTK-M takes care of setting the worklet up with the data that it needs. Forcing user code to go through a method to access field data has some costs, namely loss of vectorization. The overhead cost of setting up and managing worklet execution appears to be quite significant on both CPU and GPU platforms. It comes as no surprise that there's a cost associated with platform portability. In the OpenMP case, one cost is the use of pragmas to manage parallel regions in the code and specifying device offload attributes and data segments, and so forth. Some would say that a pragma-based approach is not truly platform portable if you have different pragmas for different devices. In the VTK-M world, one needs to recast algorithms as sequences of data parallel primitives, which may also include explicitly writing new worklets, as we've done here in this study. One benefit of the VTK-M approach is that once your code is adapted to the world of VTK-M, it can run in parallel on different backends without further modification, and VTK-M manages all of that for you. The approach that we used in this study is to measure the performance impact of platform portability in the form of hardware performance counters. Of these, a count of the number of instructions executed was a useful metric for comparing overhead cost differences in a very direct way, as opposed to trying to infer those costs from source code. VTK-M's design patterns center around data parallel primitives. Our implementation uses the worklet model rather than recasting the stencil code as sequences of data parallel primitives like map, scan, sort, etc. One could argue that the field map worklet and the point neighborhood worklet code is indeed a map operation in a functional programming model. An open question is whether or not our implementation might have performed better if we recast the computation into one or more of VTK-M's device algorithms. This particular study focuses on two platform portable coding environments, VTK-M and OpenMP. There are plenty of others that warrant examination, and doing so will make for interesting future work. The algorithm we used in this study is a straightforward implementation of a stencil kernel. One could think about instead using a separable convolution where, in the 2D case, the rows are processed first and then the columns. In that case, the number of numeric operations would be reduced, but there would be an increased overhead due to the fact that one worklet would first process the rows and then the next would process the columns. The work in our study here builds upon prior work in several different trajectories. Given the significant interest in platform portability, there have been works looking at platforms like VTK-M for different types of algorithms. In most of these, the primary performance metric has been runtime, or its derivative. Our study includes the use of hardware performance counters in conjunction with VTK-M on two different platforms, and also includes a comparison of OpenMP code on CPU and GPU platforms. The Stencil algorithm has been well studied, most often in the context of numerical solvers. One thing that's novel here is using VTK-M as the basis for doing stencil code, and we've presented two different implementations in VTK-M. It appears that heterogeneity in computational platforms is here to stay, at least for now. The result is that systems will continue to grow in complexity, and as a result, platform portability will remain an important topic in the computational landscape. Because platform portability is not for free, our work has investigated the cost of platform portability using two different platform portable approaches on two different computational platforms. The study shows some very clear evidence of costs associated with platform portability. These costs were apparent in runtime, but were clearly indicated by hardware performance counter data, particularly the count of instructions executed. We've just scratched the surface and intend to broaden scope to include study of additional platform portable coding environments. Thank you for your time and attention. I hope we can do this in person next time. Good day, everyone.
Okay, thank you, Wes. Once again, if you're watching live, I encourage everyone to, if you have a question, please type it into Discord and we'll be happy to answer it. While we're waiting for questions to come in, Wes, I'll go ahead and ask us a couple. My first one is, did you try using the OpenMP pragmas for vector instructions? Because I didn't see those in sort of the test code that you put in. So
no, we didn't. Yeah, no, we didn't do that. We just used in the paper. There's a list of compiler flags used for the Intel compiler on that platform, and the stencil size was actually pretty large, and so the vectorization rates really the larger the stencil size, the better the vectorization rate, both for the OpenMP code and the field map worklet code.
Yeah, actually, that was sort of my next question. How big were the stencils?
So in these runs, the stencil was 101 squared.
101.
So it was pretty big.
Right. So,
yeah,
yeah, over like 10,000. I do my math right.
yeah.
Okay,
Yeah.
so I guess one of your conclusions, at least for CUDA, was that VTK-M was running many more instructions than the OpenMP version. Do you know why it was inserting so many other instructions?
No, that's a good question, and so part of the methodology here was to collect hardware performance counters. So a lot of studies, they'll look at, runtime only or derivative of runtime like frame rate. And so by instrumenting with to gather hardware performance counters, you can look at number of floating point operations, total number of instructions, and we also showed cycles per instruction, so you can determine how expensive the instructions are. So that information is useful in sort of a apples to apples comparison of code A executes more instructions than code B, but you don't know exactly what those instructions are. And what we're doing is we're making an assumption here that the extra instructions are associated with the cost of setting up the worklets. And in the case of the point neighborhood worklet, presumably there's a lot more metadata that has to be set up for those worklets.
Yeah, I have to say, I'm not sure it has to do with everything to do with setup, because you run the setup once, and then you're running 10,000 instructions. I would expect that to get amortized, and maybe you could look into that by changing the kernel size and see if that affects sort of the instruction, comparable instruction rates. I would think that for some reason the CUDA compiler is inserting instructions in that loop, that the inner loop that's going over the kernel, which is the exact same C++ code as compiled for the the CPU version. And it might be something like register spilling, where the VM worklet, like you said, has a larger setup and it ran out of registers, and now it has to introduce a bunch of instructions to pull data in and out of shared memory. And so
we'll be in touch for the next version of this paper, and you can help us out.
Yeah, I think we may to get further, we have to actually look at the instructions that will be created.
Yeah.
All right. So I wonder if there's any other questions that are coming in. I don't think anything is on Discord. So I think this is a good time to sort of end the session. Let's thank all of our speakers one more time. I think this is some great work that was presented today. And I hope everyone enjoys the rest of EGPGV and EuroVis. Thanks, everyone.